All right, continuing with Math 1, 513 problem review. So we're on number 4. Number 4 is asking us, how many lines of symmetry does an isosceles triangle have? So we're looking for lines of symmetry for an isosceles triangle. And it's hard to spell. Isosceles triangle. So let's first figure out what is an isosceles triangle. So an isosceles triangle, remember, we can look like this. We can look like that. We can look even like really pointy like that. All right, what do these things have in common? Well, isosceles triangles have two sides that are congruent. So I'll even mark it a little different. Right, so 3 different triangles, the 2 sides are congruent. These are called my base angles. Base angles are the same. And we learned that if we open up the triangle the same amount on both sides, the angle is the same because the opposite side is the same. Okay, so we're going to learn that a little bit later, over and over. All right. So if I look at these isosceles triangles, lines of symmetry for an isosceles triangle, I'm just going to pick the middle one. Whoops. Actually, that's looking a little bit too equilateral. Looks like all the sides are the same. Let's break it this way. All right, so we know these are the same. All right, so if I'm looking for lines of symmetry for this, how can I break this up? It's very obvious that we could break it up. Whoops. Up and down here. That's a line of symmetry. This side is the same as that. Okay. Now, if I break it up this way, no, the top and bottom are going to be different. Top will be a triangle, the bottom will be a trapezoid. If I break it up this way, no, we could see that's not going to make equal triangles. This one becomes much slimmer. That one's wider, right? There's no way to cut it that way or that way. So actually, in a line of symmetry, how many are there? For an isosceles triangle, there's only one line of symmetry. Okay. All right, here we go. We're on number 5 in our problem set. It asks for the line of symmetry, how many lines of symmetry for a scalene triangle. So let's remember, what is scalene triangle again? So let's look at the different kinds of triangles. We just learned that we can have an isosceles, okay? We can have a right triangle of many kinds of varieties. That just has a right angle, right triangle, okay? We can have a, let's see, right triangle, isosceles. We can have a equilateral triangle, right? That has all the sides are the same. Equilateral. Lateral. Oops. Okay. And let's see what else. The last one is a scalene triangle. So a scalene triangle is kind of unique. Scalene triangle has, actually it is unique because all the sides are different. So this is a scalene. All sides and angles are different. Okay, so it's a little weird. It's a weird triangle. Let's draw another. It's too right. That's fine. All right, scalene, all different. All right, now let's think about it. First off, a scalene can be it can vary. It could look very different. We can have a scalene like this. We can have a scalene like that, right? We can have all these different kinds of scalenes. So we want to make sure that, we kind of make a rule that would work for all of them. So how many lines of symmetry for scalene triangle? Well, let's look. If I try to break this up, no, that doesn't break it up. No, that doesn't break it up because it'd have to be exactly the same on both sides. We aren't finding that here if we break it up. This one looks pretty close, but it's never going to be the same because we don't have any sides of the same, so that the symmetry is off. Symmetry is off. So when we have a scalene triangle, there's nothing in common. There's no way, if you have a shape that has no regularity to it, it's impossible to break it up evenly. So if I look at this, we're going to say no lines of symmetry. All right, that's a key. That's for scalene. Okay, so just remembering different kinds are different kinds of triangles. All right, next we are looking at number 6. All right, so 6 is looking at this. It's kind of complex, but look, we're talking about a rotation. A rotation is just where we rotate a shape, right, about a certain point. So this would be rotating about the center. It's just rotating this pin around the center, right? This would be rotating around another point. This would be rotating around another point. So we can see that based on your center, you're going to be rotating around it. Okay, so what we're asked is, what's the smallest number of degrees, right, needed to rotate a regular, this is important, regular pentagon around its center. This is a key word too. Onto itself. Onto itself means it exactly matches, okay? So you could see that if I rotate something, let's see, if I have this box right here and I rotate it, let's say that I rotate this 90 degrees. Does it have the exact same shape as before? No, okay? So this is with a rectangle though. If I am using a pentagon, I gotta think about it a little bit more. All right, so let's say that I have this pentagon. It's a regular pentagon. Remember, when it's regular, what does that mean? When it's regular, we're talking about all the sides are the same. All these angles are the same too. The vertices are going to be the same. So if I look at this, I'm going to have what's the smallest number of degrees needed to rotate the regular polygon around its center. Here's my center, okay, onto itself. So I wish this was drawn a little better, but it's not. But if you look at this, if I rotated this 180 degrees, this part, we can think of it rotating like it's a spinner. This would rotate all the way down, and I would end up with something like this. This bottom flat part would be on the top, right? And I'd end up with, it would just be inverted, right? Instead of facing up, now it faces down. Okay. So if we rotated it, let's see, 100 degrees, or excuse me, 360 degrees, guess what? Where do we end up? We end up back onto itself. But the thing is, I don't think this is the smallest number of degrees I have to rotate, because if I go all the way around, that's 360 degrees. Now the thing with this is, we want to find the smallest number of degrees needed to rotate the regular polygon around its center onto itself. Okay, so if it's rotating onto itself, essentially think about it this way. All these angles, right, are the same. The shape is exactly the same on all sides. It's not drawn perfectly, but it's exactly the same. This would be a pentagon that is not exactly the same. 1, 2, 3, 4, whoops, 5. You see, this is a pentagon as well. 1, 2, whoops, 1, 1, 2, 3, 4, 5. But it's not a regular pentagon. That's a regular pentagon. So watch. If I rotate this point here, if I just rotated it so that it was in the position of this, right? Think about it. Rotate it. We rotated that so it was in the position of the other one. We could see and visualize, this is not hard to visualize, but it would line up onto itself if I rotated it this degree measure. And we could see that, you know, these are the vertices. So if I rotate it this far, and then to this vertice, and then to this vertice, then vertice, then this vertice, how far is it to go all the way around? There's 360 degrees, right? So if I want to just rotate this little portion, I want to start here around my center, rotating it so it aligns with this vertice. I need to think about it. Well, how many turns are there to go 360? And these are all equal because the sides are equal. We got 1, we got 2, we got 3, we got 4, we got 5. So what I'm going to do is take the 360 and I'm going to divide it by 5, right? So we end up with 72 degrees, okay? So each of these is 72 degrees, and if we were to make, you know, all these vertices kind of go towards the middle, this would be a rotation of 72 degrees. What? So that's 72, that's 72, 72, 72, 72. All those add up to 360. So we know we just have to rotate it this far to have the whole thing line up. Okay? That's a little tricky. The main things for this is we're talking about regular polygons, so all the sides are the same. Okay, it's a regular shape. We want to rotate around the center onto itself, so we're rotating it so that it fits exactly on itself, so that it's lined up exactly on itself.